Hello. All right, check. Okay, we're streaming. Share. Copy. People. Check, check. All right. Okay, guys. Are you here? Anyone in the chat? Let's see. Need to go. Check, check. Anyone here yet? All right. I will post on Blackboard as well. If anyone's in the chat, hold on. I'm just going to post the link on Blackboard first. Should have logged in before I did this, but we're all learning. Hey, Carly, how you doing? I see you there. Okay. Can you see me in the upper left corner? Maybe. Hold on. Let me do this. Okay, hold on. All right. Okay. All right, so hey, Carly, how you doing? All right, let's see. And if you have questions, feel free to email me as well, and I'll answer them that way. But I just wanted to go over the problem set if anyone is interested in asking questions about the latest problem set. So let me pull that up, I guess. Let's do this. I'll do that. Okay. So, okay. All right. I'll wait a few minutes and see if anyone's there to ask questions. Carly, do you have any questions, Carly? If you do, that's fine. Let's see. I see some people viewing it. Does anyone have questions? I don't know exactly what we should go over here. I guess I'll just hit the highlights, and then if you have questions, let me know. So let me go through the problems on the problem set, and we'll talk about. Hi, Nick. How you doing? It's a little chilly, but hopefully it's warming up. Let's see. All right, so for the electrochemistry problem set that you might have gone through, or at least you just looked at the key, I guess the couple highlights to hit you with are just, the components of a galvanic cell. So, for instance, if you go into number 2041, I kind of sketched it out. You didn't need to do that to answer the question, but you need to sketch it out to see what's happening. So, in that one, we looked up the reduction potentials for both copper and tin, and we saw that tin had the lowest reduction potential. So that means that reaction, the one I'm highlighting here, is going to be actually reversed, and that's going to undergo oxidation. So when we reverse that, that flips the sign to positive. We add the two together, and we get the overall cell potential for that reaction. Okay, and so a couple things to note. Notice in the full reaction that the electrons canceled out, and that needs to happen. If the electrons don't cancel out, then your equation is not going to be balanced. And then another thing is but another thing to note is it's nice to write the half reactions so you know how many moles of electrons are actually being transferred. Okay, so we got copper is going to require 2 electrons, but if we look at the reverse of the tin reaction, that is going to actually produce the 2 electrons. So the tin's going to produce the 2 electrons, and those 2 electrons will then go to the copper ions, and then the copper ions will be produced, right? And that's kind of illustrated here, but you don't see the electrons. So it's good here to see the electrons, and the number of electrons there is going to be important when we get to the Nernst equation later on. When we look at N in the delta G equations on your formula sheet, the N refers to the number of electrons, and so in this case N would be 2 because it's 2 moles of electrons being transferred. Okay, so if we made a battery out of the copper and tin, we'd have tin 2 plus in solution over here, and we'd have tin solid electrode, we'd have a copper solid electrode, and then copper ions in solution over here. And so what would happen is the tin would be oxidized. So this tin right here, the metal piece, will push its electrons across the wire. Whoops. Okay, pushes the electrons across the wire over to the copper. The copper is going to not react with the electrons, but it's the copper 2 plus ions that will react with the electrons, and they will reduce the copper on to that copper metal. So notice the copper ions in solution here are going to be placed onto the metal copper electrode as solid copper neutral atoms. Okay, and an important thing to note is as the tin pushes its electrons across the wire towards the copper, it's going to start dissolving as tin 2 plus ions in solution over here. So the electrons are flowing from the tin to the copper, but this solution is going to become more concentrated with tin 2 plus, and this this solution is going to become less concentrated with copper as the reaction proceeds. Okay, and just a couple of vocab things. We call this the anode. That's where oxidation occurs. We call it the anode, and we call this the cathode. That's where reduction occurs, and electrons always flow from the anode to the cathode spontaneously. Okay. Now we give the anode a negative sign, so that's the negative side of the battery, and we give the cathode the positive sign. That's the positive side of the battery. But we call the anode the negative side is because that's where electrons are being produced. That's where the negative charge is being produced, and they are flowing towards the positive side, where they're attracted to the cathode. So anode to cathode. Okay, but a couple things, just going on here, yeah, you can sketch the battery, you can sketch the galvanic cell, but you don't need to. You can just look at this. You're losing, as the reaction proceeds from left to right, you're losing tin in the form of tin 2 plus, and you're gaining copper. The copper 2 plus is becoming copper. So the solid tin electrode would be decreasing in mass, and the solid copper electrode would be increasing in mass as the reaction proceeds. Okay. So let's see. So that answers those questions. But it's important to know what we get from these reactions. We can set up a battery. Okay, everything from the reduction reaction has to go in the cathode side. So note the cathode side of my battery has solid copper and copper ions, and those were the two things that are part of my reduction reaction. And then my oxidation reaction has tin, solid tin in tin 2 plus ions. So on that side, on my anode side, I have to have solid tin and tin 2 plus ions. Okay. All right. Any questions so far with that? If anyone's watching, I don't know. I guess I'll check on that. Yeah, okay, we got some viewers. If you have a comment, or if you have a question, you can comment it, or you can email it to me at fcps.edu. Don't email me at the Google one, because I'm not currently checking that. Just the fcps.edu one. Okay. So we'll keep going, and I'll just highlight the different things that are important here. Okay. Let's see. I wasn't able to find, where would I be able to find that? Okay, so Appendix E, I gave you a copy of that, but if you don't have it, remember, it looks like this. It's in your book. It's in the back of your textbook. It's the appendix in your textbook. And it's somewhere in the back there. I don't know, let's see. Does it have a page? Yeah, page 1064. There you go. That's in your textbook, okay? Okay. Is the voltmeter always going to have a positive reading? The answer is yes. The voltmeter is always going to have a positive reading if it's flowing from the anode to the cathode. If you switch, but you have to have the right, so the voltmeter has to be hooked up to the right side. So you have to have the negative side to the negative side and the positive side to the positive side. And when that happens, the voltmeter will be positive. And if you switch the wires, the voltmeter will be negative, but it's just because you switched the wires in the voltmeter, if that makes sense. But the voltmeter for a spontaneous reaction, it has to be positive. So the reaction is only going to happen in the spontaneous direction without any outside intervention. So without plugging it in, recharging your battery, the voltmeter always needs to be positive. Okay, so. All right. So when you're just trying to figure out what the redox reaction that's going to be, if you look at 20.42, again, you're looking for the lowest reduction potential. So if you looked up the reduction potentials again in Appendix C, and you can probably just Google some of these reduction potentials. You probably have, if you Google them, you might not get the exact numbers that are in Appendix E, so they might not match up the problem set in your book, or the answers to the answer key in the back of your book, but you probably get close enough to them to understand what would get oxidized, what would get reduced, that kind of thing. So here, the cadmium would end up being oxidized, so we'd reverse that reaction. It's always good to write down the overall reaction, just so you can visualize what's going on. But again, the reason why it's important to have the two half reactions is because you want to know how many moles of electrons are being transferred. And again, that's going to be important for the next questions that you'll see when trying to figure out what the delta G is for the reaction, or using what we call the Nernst equation. Okay. Oh, I got a question, maybe. Let's see. How do you know which half reaction will flip? Okay, so which half reaction will flip is the lowest one, because your overall potential has to be positive. So for instance, if we're looking at here, we're looking at this reaction, we have this reduction potential has a negative 0.403 volts, and this reduction reaction has a positive volt. If we flip this one and the chloride would be oxidized, that would give us a negative plus another negative, and we would have an overall negative potential. You're going to flip the lowest one, so you always end up with a positive potential. That's going to be the spontaneous reaction. Now, it doesn't mean to say that the reverse reaction can't happen. So cadmium 2 plus could be reduced by chloride, and chloride could be oxidized by cadmium 2 plus, but you would have to supply that much voltage at least to cause the reverse reaction to happen. So the positive voltage value is telling you the spontaneous one. So if I mix these two reactants together, cadmium and chlorine, that positive voltage is telling me that reaction will happen. If I were to mix cadmium ions and chloride ions together, the reverse reaction won't happen spontaneously. I'd have to add in some electricity. If I supplied that solution, if I had a solution that contained chloride ions and cadmium ions, I could zap it with some electricity, and as long as that electricity is greater than that voltage, then we could cause that reaction to go in reverse. Okay, but how do you know to flip which one to flip? You flip the one that's the lowest one, so that you ensure that when you add the two together, E-ox plus E-red, you end up with a positive value. Okay. Yes, okay, so reversing the spontaneous redox reaction is recharging the battery. Exactly. So if this is my battery, if I made a battery out of cadmium and chlorine, this is what my expected voltage would be initially. And as the reaction proceeds, so think about this, so the amount of chlorine is going to decrease, and the amount of cadmium ions and chloride ions are going to increase, and that's going to decrease the favorability of the forward reaction. As you increase the amount of product and decrease the amount of reactant, you're decreasing the favorability of the forward reaction, and you're increasing the favorability of the reverse reaction. So the voltage goes down, goes down, goes down. So as the reaction proceeds, your voltage starts out at its highest possible potential, and it starts to go down until it doesn't run anymore. And recharging the battery is plugging it in and supplying a voltage that's greater than the spontaneous voltage of the forward reaction, and that can trigger the reverse reaction. So recharging the battery is causing the reverse reaction, but the only way you can do that is supply a greater voltage than what the spontaneous reaction requires, or produces. So the spontaneous reaction for this reaction produces 1.762 volts. If you supplied a voltage greater than that, then you could cause the reverse reaction to go, and that's what recharging the battery is. Okay, so like for this reaction, we would have to supply a voltage greater than 0.473 volts. Okay, the higher the voltage, the faster you can charge the battery compared to the spontaneous voltage. But yeah, so that's exactly what we mean by recharging the battery. Okay. Okay, so let me see. I got another question. Let's see. Okay. So is E cell always going to be positive for any redox reaction? Yes. Okay. So the cell potential, if cell potential isn't positive, then that redox reaction is not spontaneous at those conditions. That's what that would mean. Now, that degree sign, the E naught cell or standard cell, that means at 25 degrees Celsius, 298 Kelvin, and the solutions of your the concentrations of your solutions of the galvanic cell are 1 molar. So we can change what the potential is going to be based on concentrations and stuff like that, and temperature. And we're going to get to how we do that, or how we can calculate what the new potential will be using the Nernst equation here in a second. But for a battery to work, it's got to be a spontaneous redox reaction, and a spontaneous redox reaction has to have a positive cell potential. So it doesn't mean all redox reactions have a positive cell potential. It just means the only ones that are going to be spontaneous have a positive cell potential. So if you're going to, like if I threw all of this stuff in the pot together, if I threw cadmium, chlorine, chloride ions, and cadmium ions all together, the chloride and the cadmium wouldn't react to produce chlorine and cadmium, or sorry, the chloride ion and the cadmium ion wouldn't react in the reverse reaction to form chlorine and cadmium spontaneously, but the forward reaction would. The cadmium and the chlorine will spontaneously, cadmium will spontaneously be oxidized by chlorine, and chlorine will be spontaneously reduced by cadmium, but the other way won't happen. It doesn't mean it can't happen. It just has to be supply. You just have to supply a voltage higher than the spontaneous, the voltage of the spontaneous reaction. Okay. But yeah, for a battery, you have to have a redox reaction that has a positive cell potential. Okay. What is PT? Okay. Platinum. Okay. So that's a good question. Okay. And after we go through the problem set, I want to do the, I want to look at the voltaic cell practice stuff, just so you can sketch a voltaic cell. But the important thing is you always have to have a solid electrode at each station. So you have to have a solid electrode that's the anode, and you have to have a solid electrode that's the cathode. And if you don't have a solid in your half reaction, you need to pick a solid that's a good conductor of electricity, but won't react. That's kind of inert. And platinum is a really good metal. So whenever you need a solid metal that's not part of the reaction, that won't react, but is a good conductor of electricity, just pick platinum. So let's go back up to here, okay? So if I'm constructing this battery here, I'm using tin as my solid electrode at the anode here because I have solid tin in my half reaction, right? So my oxidation half reaction has a solid metal. So if my oxidation half reaction has a solid metal, I'm just going to use that metal as the electrode. And so, and same thing with my reduction reaction. My reduction reaction has a solid metal, the copper, and so that means copper can be my electrode at the cathode. But if you go to this one, if I was making a battery out of this reaction, notice I don't have a solid in my reduction reaction. Notice that I have chlorine, I have 2 electrons, and I have 2 chloride ions. Chlorine's a gas, I have 2 electrons, and chloride's going to be aqueous in solution. So what we're going to have to do is we have to pick a solid electrode that's going to work as a good conductor of electricity, but is not going to react. And that's when we pick platinum, okay? So technically, you could say chlorine is the electrode at the cathode, but you would need a piece of metal there, and that's why we chose platinum. So whenever you need to choose, whenever you don't have a solid to pick from, use platinum. Okay, just that's kind of understood that that's the metal that you would use. But you could use gold or maybe gold, palladium or something like that. But platinum's usually the go-to. Okay, so hold on. But when are we finishing all of the units and preparing for AP exam? Also, where are we going to start from? So, yeah, Thomas, okay, so real quick, I have no idea. Like, I can't assign anything new, but I'm still going to assign you optional new content, but I can't grade you on anything. I have no idea, man. So, you know, what they announce to you is what they announce to us. I don't know if I really should be live streaming with you guys, but I don't find any harm with it. And they said we could use the Google Suite, and YouTube is a part of that. So that's what I'm trying to do. So I'm going to keep preparing you, and I want to introduce all the stuff. But when we get back, you know, we might be told that, you know, I guess technically, I guess depends on how many people actually keep up with the content, but we might have to relearn it and stuff like that. I'm going to give you practice tests and stuff online that you can work on. It'll be strictly optional. And you know, later on, as we get closer to the AP exam, you know, I have a feeling you know, they're probably going to have to postpone it or something. But if they don't, we'll try to figure out something. You know, right now we're not allowed to meet, but maybe in a couple weeks we'll be allowed to meet, and we can meet at the library. And I have all the practice tests, and so maybe we can do practice tests and stuff like that. But let's not. Let's just try to stay on top of the material and practice what we can practice. And maybe I'll assign some practice stuff on the College Board classroom that'll help you, you know, review older material. But until then, I just don't know. So we'll cross that bridge when we get there. But don't sweat it. I mean, you know, I know third quarter is the biggest part of your grade, but third quarter is going to either be extended or something's going to happen. So those percentages will change. So I wouldn't sweat that too much, but not 100% sure. Okay. So does platinum work as a solid for both the anode and the cathode? Yes, you can use platinum anytime you need a solid electrode, either at the anode or the cathode. So if your oxidation reaction doesn't have a solid, then platinum is going to be your anode. If the reduction reaction doesn't have a solid, then platinum is going to be your electrode at the cathode, if that makes sense. Okay. Okay. All right. So let's keep going. Okay. So notice. Okay, so for 2053, we were using our delta G equals negative RT natural log of K. So just remember that when you do solve using this, your delta G is going to be in joules. So if you want it in kilojoules, just divide by 1,000. But then we're doing this new equation that we haven't done in class. And this equation is on your formula sheet. It's delta G equals negative NF cell potential. And sorry, so N is moles of electrons being transferred. So that's why it's always important to write out those half reactions and know what the balanced amount of electrons would be when you add up the reactions so that electrons cancel out. So like if it ends up being 10, then your N in this equation is 10, okay? So N is moles of electrons. F is Faraday's constant. That's on your formula sheet. It's 96,485 joules joules per coulomb. No, that's not right. Sorry, 96,485 coulombs per mole of electrons. Joules per coulomb is what a volt is. Okay, so again, Faraday's constant, 96,485 coulombs per mole of electrons. Okay, but it's on your formula sheet. But that's where when you see F in those equations, it's Faraday's constant, okay? So you would just plug those in, and you would get your voltage. Make sure, again, just like in the delta G equation up here, negative RT natural log of K, just make sure that you understand that delta G has got to be in joules, not kilojoules, okay? Are there... Are both equations the same? Which equations? No, well, this equation is, well, I mean, yeah, if you want to, you can say negative RT natural log of K equals negative NF cell potential if you want to. You could set this part of this equation equal to that part of that equation. But this is the equation we would use if we have equilibrium constant and we want delta G, or we want delta G and we need equilibrium constant. And this would be the equation we use if we have delta G and we want cell potential, or we have cell potential and we want delta G. Does that make sense? Does that answer your question? Okay. Okay. But are you talking about these two equations? Or are you talking about the half reaction equations? The Fox Warrior? Did I answer your question there, or? Okay, just let me know. All right, I'm moving on here. So notice, you know, in Okay, good. All right. Um, okay, so now we have a new thing called the Nernst equation, and it's this equation here, and unfortunately it is not that equation right here. I would memorize it. It's in your guided notes in the PowerPoint, in the electrochemistry PowerPoint. You might want to go back and look at it there. I would memorize it to use it, but we'll talk about how you can if you just understand this value of Q here, if you can understand that value, yeah, no worries. I guess is the stream okay? I guess it's lagging. Maybe okay. We'll maybe I shouldn't be outside. Maybe that's my internet connection. If I go inside, it's just going to be the dog barking, and my daughter is doing her kind of home in schooling thing. So just came outside, even though I'm getting a little cold. All right. Okay. All right. Let's keep going. Keep going. All right. All right. So let's go back here. Oh, nope. All right. Okay. So this is the Nernst equation, and so notice the difference between you got E and you got E naught, right? So this is standard conditions. This is cell potential under standard conditions, and this is the potential if you're not at standard conditions. So remember, for your battery, for your standard galvanic cell, you have to have 1 mole. Your concentrations of your ions have to be 1 molar, and you have to be 298. So what I want you to notice is that for these two questions, for non-standard conditions, notice they didn't change the temperature. Yeah, so your battery is going to operate differently when it's hotter versus when it's colder. But this is just about changing the concentrations. So it's really about what this Q value is here, okay? So the first thing is, if I'm going to use this equation, notice that I have RT over NF. Well, NF here, that's N is moles of electrons and F is Faraday's constant. And so this is moles of electrons. So it's really important that we look at the reaction and see the balanced amount of electrons being transferred here. And the balanced amount of electrons being transferred here is 2 electrons. So when I'm plugging stuff in, if I'm plugging stuff into the Nernst equation, my N value is going to be 2. And also notice if I'm plugging in for the Nernst equation, I have to know what my standard cell potential is. So that's where you would use your appendix C. You would use your standard reduction potentials. So the zinc's going to be oxidized and the nickel is going to be reduced. So if you look up the zinc reduction potential, it's negative 0.763, and so this is the oxidation potential. So that's positive 0.763. Okay. So, and so this is the standard potential. So when you're using those potentials in appendix C, you're getting E naught. So what does E naught mean? That means standard. Standard means standard conditions, 298 Kelvin, and 1 molar for your concentrations. Okay, standard conditions for thermodynamics and electricity. It's not the same thing as STP. It's not the same as standard temperature and STP. Standard temperature for gases is 0 degrees Celsius. Standard temperature for thermodynamics, so anything delta G, anything delta H, anything delta S, and for electrochemistry, so cell potential, E, standard temperature for those things is 25 degrees Celsius, 298 Kelvin. So what this voltage is right here, what this represents is this would be the voltage if I made my battery and I constructed it out of standard conditions. So if the solutions were 1 mole and I was running the battery at 298 Kelvin. So this E right here, without the degree sign, is the potential at any conditions. So notice how we can adjust it. There's a place to plug in the new temperature. So if I wasn't at 298, I could plug in the new temperature and see what happens, right? And if Q is the same thing as our equilibrium constant, or equilibrium expression. So if I adjust my concentrations, I would be adjusting this Q value. Okay, so what I'm going to do here, is for part B is just plug in those values for the Nernst equation. So this is our standard cell potential. We got those from the reduction potential. No, it's not on the formula sheet, Mason. So that's one that you might have to memorize. Now I'm gonna show you what you really need to know here in a second about the Nernst equation. So since it's not on your formula sheet, that means on the AP exam, you're not gonna have to actually calculate the new potential, but what you're gonna have to do is figure out, is the new potential, the non-standard potential, is it gonna be greater than or less than or equal to the standard cell potential? And if you know the Nernst equation, you could just plug in and figure it out that way. But I'm going to tell you how to use Le Chatelier's principle, or this Q value and Nernst equation to figure out if it's going to be greater than, less than, or equal to. But it's not on the formula sheet. I suggest you memorize it. But we'll talk about different ways on what to do if you're not going to have to calculate the actual new value like you did in this problem set, but you will have to say, will the potential increase or decrease or remain the same? Will it still be the standard, or will it be greater than the standard, or will it be less than the standard? Okay. So again, Q is just equal to the equilibrium expression. So notice Q in this reaction would be the zinc ion concentration over the zinc 2 plus concentration. Now I didn't write out the full reaction, but zinc 2 plus ions are a product, nickel 2 plus ions are a reactant, and remember the equilibrium constant is products over reactants, and you don't include the zinc or the nickel here because those are solids, and we never include those in the equilibrium expression to begin with. So the equilibrium expression K for this reaction would be K equals the concentration of zinc ions divided by the concentration of nickel ions. Okay, well, that's what Q is equal to. Okay, and so, whoops, all right, where did I go? Okay, so they gave us, so we calculated the standard cell potential using our reduction potentials, so we figured that out. 2 is the moles of electrons being transferred. F is Faraday's constant, so 96, 485. Again, that's on your formula sheet. And we got to understand that we didn't change the temperature, so we're still at 298. The only thing we did change was we adjust those concentrations. So again, that's what Q is equal to here. It's the zinc concentration over the nickel concentration, 0.1 over 3. So you take the natural log of that ratio, you multiply it by this, and then whatever that comes out to be, you subtract it from the 0.483, and you get your new voltage, okay, at the new conditions. Now let's talk about this in terms of Le Chatelier's principle. Okay, if you look at the overall reaction, right, zinc is a product and nickel is a reactant. Now let's think, at standard conditions, those concentrations are both 1. So what would Q be there? It would be 1 over 1. Okay, so those are standard conditions. All right, and so what did we do? Standard conditions are, each concentrations are 1 molar, but what did we do here? We lowered the concentration of the products, and we increased the concentration of the reactants. So what are we doing by increasing the concentration of reactant and decreasing the concentration of product? Think of it in terms of Le Chatelier's principle. We're pushing the reaction to the right. We're increasing the favorability of the forward reaction. And if you increase the favorability of the forward reaction, you're going to decrease the delta G. But what does that mean? It means you're going to increase the potential. So if you cause a Le Chatelier's principle shift to the right, towards the products, cell potential will increase. If you cause a Le Chatelier's principle shift to the left, you're going to decrease the favorability of the forward reaction, and that means cell potential is going to decrease. Okay, but also if we use the Nernst equation, if this is 1 and this is 1, if you get 1 over 1, what's the natural log of 1? Does anyone know the natural log of 1? it's 0. And then so you get 0 times 0. And so then you get cell potential minus 0. So that's another thing to understand. When Q equals 1, and what is Q? It's a ratio of products over reactants. It's the same as the equilibrium constant. If Q is equal to 1, then cell potential is going to be equal to standard cell potential, okay? But let's look here. What's Q in this value? Q happens to be less than 1. So what does that mean? It means when Q is less than 1, your new potential is going to be greater than the standard. And that's what ended up happening, right? Q was less than 1. The ratio of product concentration over reactant concentration was less than 1, 0.1 over 3, right? Q's less than 1. So when Q's less than 1, the new cell potential should be greater than the standard. And look, the new cell potential was 0.5, 0.527, 0.53, and the standard cell potential was 0.48. So when Q is less than 1, cell potential is going to be greater than the standard. And so what does that mean? It means if Q is greater than 1, then the new cell potential is going to be less than the standard cell potential. So you can just use Le Chatelier's principle if you're just trying to figure out greater than, less than, or equal to. But you have to use the Nernst equation to actually plug it in. But let's move forward. If you look at the next one, notice that the Q value for the next one, Q is greater than 1, 0.9 over 0.2. So Q is greater than 1, and so the cell potential should end up being less than, and it ends up being less than, okay? So this is the actual value, but a lot of times you're not going to have to actually calculate the value, or at least, no, so from now on, like on the AP exam, you're not going to actually have to calculate the actual value. You're just going to have to tell me if it's greater than less than. So now you know if Q is greater than 1, the new cell potential is going to be less than the standard. Okay, does that make sense? Okay, can anodes and cathodes be classified as products or reactants? Yes, they can be if they're part of the reaction, right? So if we go, can anodes and cathodes be classified as products or reactants? Yes. If we go back up to our battery here that we made, right? Solid tin is a product, so solid tin is a product. Solid tin's a reactant, so solid tin's a reactant in our battery, in our galvanic cell. So that anode is part of our reaction, okay? And copper was one of our products, and solid copper our cathode electrode, and so yes, it would be the cathode would be a product of this reaction. Okay, now understand that this isn't when you're making a battery, when you're making a galvanic cell, it's not the type of reaction where you only start with reactants. You have to have all the parts of the reaction combined. So that means all the reactants, all the products have to be a part of the setup of the battery. And then when you connect them, you get the spontaneous flow of electrons. Okay, so it's not the type of reaction where I just start with reactants and I get products. Yes, if I have tin ions and if I have tin and copper ions, they'll spontaneously react together. But to make a battery out of that, to get electron flow out of that, I have to separate the compartments, and that's when I have to have all of the things in my reaction, the products and reactants, all set up to start a battery. Like this reaction wouldn't happen unless I had solid copper over here. Okay. And but also understand, so what does that mean? It means, yeah, I start with solid copper, but as the reaction proceeds, I end up with more solid copper. Yes, I start with solid tin, but as the reaction proceeds, that electrode is going to decrease in mass. I'm going to lose some of my tin. Okay. Now, if you don't have a solid, let's say this was, let's look at this reaction. Let's say instead of copper 2+ yielding solid copper, what if it's copper 2+ yields copper 1+? It would still be reduced 2+ to 1+, but I wouldn't have a solid. I would have aqueous ion. Like if this was copper 1+, right? So that's when I would decide to use platinum as my electrode here instead of copper, because I didn't have any solid copper. I would use platinum, and And then what would happen here is the copper 2 plus would be forming copper 1 plus still in solution instead of copper 2 plus forming solid copper onto the electrode. And so in that case, platinum would not be a part of my reaction. It would not be considered a product. It would just be, what is allowing for the flow of electrons. Okay. So in that case, so yes, the anode and the cathode electrodes can be products and reactants, and they should be if you have solid things that can be the anode or the cathode. But if you don't have, but they don't have to be. So if you want to, you can use the platinum. Okay. Hold on. I got a couple questions. Email, I think. All right. Is Q in the Nernst equation the same as Q from Q calculations? Yes, it's the same thing. Remember, Q calculations is just plugging in concentrations into the equilibrium expression, just not at equilibrium conditions. So Q is the same exact thing as the equilibrium expression for a reaction. Okay, and so it's the same Q in the Nernst equation. And then the other question: are you going to do live streams to go over notes like a lecture to follow along? If not, could you, so we can stay ahead? Yeah, we're going to kind of maybe do that. Or I think what we're going to do is, what I'll do is post the PowerPoint and the notes, and then some practice problems that go along with it, and then I might answer questions. I'll do a live stream to answer questions, I think, maybe. I'm going to see how this works. I'm not the most tech savvy person, so I'm trying to figure it out myself. I think I might want to do some PowerPoints with voiceover and that kind of thing, but I just got to figure it out. So right now, I think the plan's going to be do this. Like after this, and maybe on Friday, we're going to have kind of covered everything, and I'll answer all your questions. We'll have covered everything in Unit 6, and then what I'm going to do is give you a Unit 6 kind of like a practice test, like a take-home test, an optional test. It's not going to be graded or anything. And I might just throw the test at you, and then we'll go over the answers to the tests in a live stream or something. And then we will start Unit 7. And I think for Unit 7, that's when I will I'll try to do, PowerPoints that have voiceover and stuff like that, so I can post, and you could take guided notes, and then it could come on and answer questions. I'm just trying to figure it out as well, though. Okay. All right. So let's go back to the Nernst equation here. Okay. Okay. So what I want you to notice is the thing I want you to notice about 2066 is notice what Q is equal to. Like if you looked at the overall reaction, right? Okay, so first off, right, what's N going to be in my Nernst equation? N's going to be 3. So for this reduction reaction, it was 1 electron, but remember, if I'm adding this equation to that equation, I got to triple this, so moles of electrons cancel out. So my N value isn't 1, my N value is 3. And then, just for example, if this were 2 electrons here instead of 1, then my N value, if this was 2 electrons in this equation and 3 electrons here, my N value would end up being 6, right? Because the N value is the balanced amount of moles of electrons being transferred. Okay. All right. So if we add these two reactions together, notice that we have 2 products that should be in the equilibrium expression, right? And notice that the Ce3 plus ions have a coefficient of 3 in front of them. So my Q calculation, I need to cube them, right? It's the same thing as the equilibrium expression. So this is my Q calculation. I got to cube that concentration, and I got to cube that concentration. Okay. So it's not always just going to be this ion over that ion. It could be this ion squared over that ion. It really just depends on the full balanced equation. So I didn't write it out here. I probably should have in hindsight, but it's always good to have your full balanced equation so you know what Q is. But notice like chromium's a solid, so that's not part of the overall expression of the equilibrium expression, right? Okay. So, so I plug in everything. Now, if you did the math here, yeah, okay, for the textbook question, you had to calculate the new potential, but on AP exam question, they'll just say, hey, here are your new concentrations. Is the cell potential going to be greater than, less than, or equal to the standard cell potential? Well, here's the standard cell potential that we calculated. And if we just figured out that Q was going to be less than 1, then we know that the new potential is going to be greater than the standard cell potential. And that's what it ended up, okay? But if we don't have to plug in and actually calculate to say it's going to be greater, we can just say Q's greater than 1, cell potential, or sorry, Q's less than 1, so the new potential is going to be greater. The new potential is going to be greater than the standard, okay? And then if you look over here, so Q is obviously less than, or sorry, Q's obviously greater than 1 here. So when Q is greater than 1, the new potential ends up being less than the standard, okay? But again, you can use Le Chatelier's principle. If you increase the favorability of the forward reaction with what you change, you're going to increase the potential. So the new potential is going to be greater than the standard cell potential. And if you increase the favorability of the reverse reaction, then you're going to decrease your overall cell potential, if that makes sense. Okay? Is the sun getting in the way? I don't know. Are you guys good? Okay. All right. So I guess, all right, I got a couple more emails. Let's see. Last week you gave us problem set 6.2 where we had to find cell potential for 6 redox reactions. And you said we should sketch the galvanic cell. Could you either post a key or go over next? Yeah, I'll post a key for that, okay? How to sketch the galvanic cell. I kind of wanted to go over that basically with this. You know, I told my honors chemistry kids that I'll be on at 11:30. We'll see. It depends on how long this goes. Okay. So okay, let's put a break on the stoichiometry part. Let's go to, since we're talking about the galvanic cells, let's go over how to sketch them, okay? All right, so kind of here's the, okay, so, all right, so if you look at this practice problem, okay, and I think I might have gone over it on Review Thursday. Oh, wait, I had one more question, sorry, before I do that, okay. Are we able to send test corrections to you via email? Yeah, absolutely. Guys, send your test corrections to me. I'm not going to be as diligent upgrading the gradebook as possible, but yeah, send me the test corrections. You know, when I get a chance, I will update. Yeah, I'll put the curve in and stuff like that. So yeah, absolutely. Email me your test corrections and that kind of thing. Okay, absolutely. Okay, so let's look at this. So let's look at this practice problem. So we have this reaction, and yeah, I'll go over electroplating here in a second. And it's kind of what's going on in the battery. It's kind of what's going on at the cathode of the battery, Thomas. That's where like when we say, you know, copper, the copper electrode is gaining mass because metal is plating on to that electrode. It's when metal ions get reduced onto a metal surface. And so as the ions get reduced onto the metal surface, they go from the metal ion to the solid metal, and then they metallically bond onto the surface of whatever metal that is conducting the electricity on, okay? All right. But real quick, let's look at this practice problem, and then we'll go into the electroplating stuff and kind of the calculations you would have to do with the electroplating, okay? So if we look at this reaction, it says copper's being oxidized, manganese is being reduced. So copper's going from 0 to 2 plus, and manganese is going from 2 plus to 0. Okay, well, if we looked up the oxidation of copper, that's a negative 0.337. And again, I'm getting this from our reduction potential as Appendix C, right? And if I look at the reduction potential for manganese 2 plus, it's negative this. So the potential for that reaction, the forward reaction there, is actually negative. So that reaction isn't spontaneous, right? Okay, but what does that mean about the reverse reaction? The forward reaction has a negative 1.52 volts. The reverse reaction has a positive 1.52 volts, okay? So delta G would be positive because the reaction is not spontaneous, right? We know it's not spontaneous because cell potential is negative. And if we wanted to, we could plug it in to that equation. We could say delta G equals negative NF cell potential, right? We could plug that in there and solve for the delta G, and it would come out to be positive. And what would N be? What would N be for this reaction? What would be the moles of electrons being transferred? I know it's delayed, so I'm going to just let that hold. Okay, if you answered 2, you would be right. 2 moles of electrons are being transferred there, okay? All right, so as we scroll down here, all right, so we had to make a battery. All right, so they set up everything. They set up everything in this reaction, but what's going to happen is instead of the forward reaction that's going to happen, the reverse reaction is going to happen because it's the reverse reaction that's the spontaneous one, all right? So if we set up a galvanic cell, right, our manganese, it's the reverse reaction that's happening, so manganese has to be oxidized and copper has to be reduced. So this is going to end up being our anode. That's our cathode, right? We would have solid manganese and manganese 2 plus ions in solution here. For standard conditions, it would have to be 1 molar manganese, right? And we'd have to have 1 molar copper over here, okay? We do have a solid in our oxidation reaction, so manganese can be our anode at our electrode at the anode, and we do have a solid in our reduction reaction, so copper can be our solid at the cathode. Okay, so that's our setup there. We need a salt bridge. Okay, so you want a salt that has ions that are always soluble. So think of your solubility rules. You want a salt bridge that are always the spectator ions; they don't really react. So think of any alkali metal with maybe nitrate or chlorate, sometimes chloride, but chloride can precipitate out sometimes. But potassium nitrate's always a good choice for your salt bridge. Okay, so the electrons are going to spontaneously flow. The electrons go this way. You get 1.52 volts. Where did we get that number? Well, that was the value of our standard cell potential for the reverse reaction, right? Positive 1.52 volts. As the reaction proceeds, manganese is going to dissolve out. So the solid manganese is going to be consumed and produce manganese ions in solution. So this electrode is going to get smaller and smaller, lose mass over time. And then this electrode here, is the sun okay? Is the sun, I don't know. Is it bothering you guys, or can you, I can see the screen, but okay. Okay. So anyway, I don't know. I'm old. I don't know how technology works sometimes. Okay, so the electrons go over, right? And they go through the copper. So understand the electrons don't react with the solid copper. They react with the copper ions that are in solution. Those electrons jump onto the copper ion, reduce it, and this is electroplating, Thomas, right? So when you have electrons being supplied by a source and you dip the metal into a solution that has metal ions, the electrons will reduce metal ions that are in solution, and those right at the surface of the metal. It happens right at the surface, right? That's where the interaction happens, right at the surface of the metal. And those metal ions will plate as solid metal neutral atoms of metal onto the surface of the metal. All right, that's electroplating. Okay, well, to do that, you need 2 electrons. You need 2 moles of electrons to completely reduce 1 mole of copper, right? Okay. Okay, so 2 moles of electrons being transferred. If you looked at the half reactions, right, just look at the half reaction. You would have copper yields copper 2 plus. Well, how many electrons would copper have to lose to go from 0 to 2 plus, right? Copper would have to lose 2 electrons, right? So it's 2 electrons being produced by the oxidation of copper. And for manganese to go from 2 plus to 0, it would have to gain 2 electrons. So 2 electrons would be produced from the oxidation, and 2 electrons would be required for the reduction. All right, does that make sense? Does that answer your question? So look at the half reactions. So where do we get 2 moles of electrons? Look at the half reactions, and remember, it's got to be balanced. So in this case, both half reactions end up with 2 electrons in the equation, but like if you ended up with 1 electron and 3 electrons, then the overall balanced amount of electrons would be 3, right? If you ended up with 2 electrons in one of the half reactions and 3 electrons in the other half reaction, the overall balanced amount of electrons being transferred would be 6. So you really would you would look at the half reactions, okay? Or you can just look at the oxidation numbers, right? Going from 0 to 2 plus losing 2 electrons, and going from 2 plus to 0 loses 2 electrons. Okay, does that make sense? Okay. All right. So essentially, this is what you have to have set up. Okay, so and the other thing to know, okay, so the copper is being plated onto, so this electrode, the cathode is getting more massive, the anode is getting less massive because it's dissolving into solution over here. And then again, let's keep adding to it. What would I have to do to recharge the battery? I would have to plug in, my wire here, plug my wire in to an external voltage source that's greater than 1.52 volts. And if it's greater than 1.52 volts, it'll drive the reaction the other way, so the electrons would flow this way, and everything would reset itself, right? And so the other thing to know is from the salt bridge, cations from the salt bridge, as the reaction goes, as this side becomes more negative because it's gaining electrons, cations flow to the cathode and anions flow to the anode. Okay? All right. Okay. All right. So let's go back to... Let's just look at the stoichiometry problem. I'll look at this. Okay, so the last one on your problem set here. So it's electricity stoichiometry. So a couple things to know. Okay, so amps are coulombs per second. Okay, amps are coulombs per second, and Faraday's constant is coulombs per moles of electrons. So here's the deal. If you can figure out total coulombs, you can convert coulombs to moles of electrons by dividing by Faraday's constant. Okay? All right? Well, to know how many coulombs you have, if you know the amps of your voltage source, if you know how many amps your voltage source is, all you have to do is multiply by the total time in seconds you apply that ampage to whatever you're electroplating. So if I apply, 11 amps for 15 seconds, then, and I want to know how many coulombs that is, then it's just 15 times 11. And then that would be total coulombs. All right? All right. So again, we'll get into this in a second. I got another question here. I know I'm delayed. I guess I just don't know by how much. So when the electrons reach the cathode, do they react with the Cu2 plus in solution? Okay, yeah, so back to this voltaic cell. Yes, when they get to solution, again, use the overall reaction as a guide to what's actually reacting and what's being produced. Like, okay, so again, when you're looking at this, it's the reverse reaction that's happening, So manganese is being consumed and producing manganese 2 plus, and copper 2 plus is being consumed and producing copper. So yes, as the electrons flow from this compartment to this compartment, the electrons aren't reacting with the copper. The copper is just kind of the conduit for the electrons to go through. And the electrons are reacting with the copper ions at the surface of the metal and producing solid copper. Well, since they produce solid copper right at the surface, that solid copper being produced plates onto the metal, as opposed to bonds with the metal that's there, as opposed to like, forming brown particles and falling down to the bottom of the beaker. All right, so it just plates right on. Okay, so this is what's being reacted with by the electrons, and the solid copper is being produced. This is what the solid manganese is what's producing the electrons, and as it pushes those electrons out, it forms manganese ions, and they dissolve into the solution. Okay? All right, so back to the problem set here. Okay? So, Thomas, for electroplating, we applied 7 amps for 2 days. So it was 7.6 amps, which is this many coulombs per second, for 2 days, and we were plating chromium. Okay? Saltbridge, I would just always choose, so if you need a solid electrode because you don't have a solid metal in your reaction, choose platinum. So if you have to pick an electrode and you don't have a solid metal in your reaction, choose platinum. And if you have to pick the saltbridge, use potassium nitrate, because or sodium nitrate or something. You use ions. Use an ionic compound that has never forms precipitates based on both rules. So like potassium never forms a precipitate and nitrate never forms a precipitate, right? So use things that are always spectator ions. So nitrate's always a spectator ion, alkali metals are always a spectator ion, chlorates and perchlorates are usually spectator ions, right? So you could use those as well. Sodium chloride works fine, but remember, like if you have lead part of your battery or something like that, right? Lead chloride could precipitate. So you want to just be careful with that. But any ionic compound could be, but if one of those ions reacts with another ion in solution, then that could be a reason why a battery doesn't work well. And they could ask questions like that, right? Like if you had barium ions in one of your compartments and you added, sodium sulfate as your salt bridge, you could end up precipitating out barium sulfate, and then the concentration of barium would go down. And if the concentration of one of your ions that's part of the reaction decreases, you can affect the potential, right? You could just go to the Nernst equation and look at it that way. All right. All right. So anyway, we're plating, we're getting solid chromium, but it's from chromium 3+. So this is important to write down. This ratio right here. It takes 3 moles of electrons for every 1 mole of solid chromium produced, right? 3 moles of electrons for every 1 mole of solid chromium, okay? So that's important to know, because that ratio is going to come into play, right? If this had been 2+, it would only take 2 moles of electrons. If this was 1+, it would take 1 mole of electrons, okay? So this is how it works, okay? So if we have amps, we need to multiply by seconds to get total coulombs, okay? Well, I had 2 days, so I had to do days to hours, hours to minutes, minutes to seconds. So here's where my amps come in. Instead of thinking of it as amps, think of it as coulombs per second. A and coulombs per second are the same thing. So it's that many coulombs per second. So if you take your total seconds and multiply it by coulombs per second, seconds cancel out and you're left with coulombs. Now what do I do? Well, now comes Faraday's constant. Okay, Faraday's constant is 96,485 coulombs per mole of electrons. So if I take my total coulombs and I divide it by Faraday's constant, that's going to cancel out coulombs and give me moles of electrons. And then once I have moles of electrons, here it's just normal stoichiometry. 1 mole of chromium for every 3 moles of electrons. And so moles of electrons will cancel out. You'll be left with moles of chromium, okay? And once you have moles of chromium, we multiply by the molar mass of chromium to get the total mass, okay? Does that make sense? All right, and then, whoops, okay. And then, so this would be the setup for the other one, okay? So, okay, so I'm gonna wrap things up here, guys, for today, just because we'll do longer, and like, first of all, let's do this. Let me know, is this time okay, 10 a.m.? Do you want to do earlier? You want to start it earlier? Would you like to do it later? later is probably not an option. Would starting at 9 be okay, or is that too early? Because I got to do another stream. I got to do it for my honors chemistry kids, and I promised them 11:30. But you know, we can make them longer. Maybe we can start earlier. I'll tell my honors chemistry kids that I'll do it theirs later. But let me know. Leave a comment or send me an email. Let me know if this time works, or would you prefer it earlier? I don't mind earlier. I get up at 5 still, so we can go early. But I kind of, I don't want to have to do it throughout the day. I'd like a time where we can reach as many people as possible. So, okay. So we'll get, but is 10 okay? I mean, I know you probably don't have much to do. So I'm guessing like any time after you sleep is okay, and I'll let you sleep in, Okay. So 10 a.m., 9 a.m., 10 a.m. Okay, that's good. I'll just tell my honors kids I'll do their live stream later on from now on, so we can have more time. Okay. But what I like you to do, go back and look at these stoichiometry setups in the problem set. Look at the key. And now that you know that an amp is a coulomb per second and Faraday's constant is 96,485 coulombs per mole of electrons, go back with that in mind and see how we're doing it. So it's just stoichiometry. It's just with a different type of conversion. So all we're doing, like if you look at 20.92, what's stoichiometry? Take what you're given and convert it to moles. Well, what was I given? I was given time in amps. Okay, well, if I'm given times in amps, I can get to coulombs, and if I get to coulombs, I can get to moles of electrons. Boom, I got what I have. I have moles of electrons, and then once I have moles of electrons, I can use my half reaction to do that mole ratio, right? But it's important to know that half reaction, how many moles of electrons are required to completely reduce a metal all the way down to its solid, right? So for magnesium, it takes 2 moles of electrons for every 1 mole of magnesium produced. But if it was sodium 1 plus, it would only take 1 mole for every 1 mole of sodium. All right, does that make sense? All right, so with that in mind, go try these calculations that I have some more practice. Okay, so what I'd like you to do for homework is do the stuff I posted. Okay, so for those of you in first period and 8th period, you took the quiz. I posted the quiz, the last quiz. I posted the key on Blackboard. Check the key out, and if you have questions, ask. You can email me questions still. We don't have to be on a live chat. You can still email me questions, or save your questions for the live stream on Friday, and then. Also, I gave you the homework quiz 6.2, which is all the electrochemistry stuff, and go through that. Again, nothing's graded now; it's all optional. But go through it. That's the way the quiz will look if we finally take it. So go through that, and I'll post the key tomorrow. And then I will go over any questions we have on Friday, and I'll do another live chat for Friday. Okay, so think of any other questions you might have for the live chat. And in fact, maybe email me your questions, and I might email me questions, and if you don't mind, I might save them for the live chat if I think they could inform more people. But yeah, email me your questions, and we will and we'll figure it out. Okay. So go ahead and do this. Also, go ahead and do concept check 6.2 or concept check 2. Go ahead and work on that as well. When you submit, I'll go in and I don't know if I have changed this. I'll go in and change it. So as soon as you submit, you'll get your results. Okay, it's not going to be graded as correctness. It's just going to be graded as completion. So go practice those questions, and I'll rechange the settings. So as soon as you submit your answers to that, you get your results. So you can, do that and maybe come up with questions with that. Okay. So, yeah, that's it. Thanks for coming out and watching. I'm going to try to figure out how to save this and upload this to like a YouTube channel or something. And, so that maybe, you can watch it, or maybe you can share it with other people who weren't able to make the live chat. But all that's going to come later on today because I gotta go chat with my honors kids about gas laws. All right, so have a good day and keep up on your chemistry. All right. All right. End stream. Let me make sure. All right. Hold on. I'm not ending just yet. I had a couple emails come in. Let me see if they are important. Oh, okay. Okay. 10 a.m. works. Okay, so we're gonna keep it at 10, guys, and but I might end up posting some other things, maybe on maybe I'll try to make some videos that aren't necessarily like a live stream to help you out with the new stuff, especially when we get to Unit 7, which is going to be brand new. But okay, so anyway, thanks for coming, and we'll see you again on Friday. All right.